Okay. Hello, everyone. So for today, I'll be presenting a paper by the title Collaborative Diffusion for Multimodal Face Generation and Editing, which published in CVPR in 2023. So the contribution of this paper is as follows. So this paper introduced collaborative diffusion, which exploits the pre-trained unimodal diffusion model for multimodal control without retraining. So this idea of without retraining is the most important thing for this paper's contribution. And this is the first attempt towards flexible integration of unimodal diffusion model into a single collaborative framework. So in the past, people have been using different kinds of unimodal diffusion framework, but this is the first time where they have to collaborate different kind of unimodal into single multimodal collaborative framework. So this framework is tailored for iterative property of diffusion model. So they also propose dynamic diffuser, which predicts the spatial varying and the temporal varying influence function to selectively enhance or surpass the contribution of a given modality at each iterative step. So the main contribution of this paper is the design of the dynamic diffuser, which maps the influence of each unimodality to the final output. So this proposed idea also demonstrates Did I click on? I don't know, something pop up. Oh, so this demonstrates the flexibility of the framework by extending to the face editing driven multiple modalities. So they try to also add another additional task so that they will also provide a face editing framework on top of the face generating framework they already have. So both quantitative and qualitative results demonstrate the superiority of collaborative diffusion in the multimodal face generation and editing. So to appreciate what they did, let's look a figure which tells about their contribution. So first, given different kinds of modality, for example, for this paper, they use a mask conditional modality and a text-based conditional modality. And using the two modality, we can generate a high quality image that is consistent with the provided mask and provided text image. So for example, if we see this multi-modal condition, for example, given a mask here and given an input text prompt, we are trying to generate a very high face quality, which is aligned with the provided mask and with the described text. For example, if you see this mask and if we see this input text, like it says like she is a teenager, then the final face synthesized that we have is someone who looks like a teenager and who has consistency with the mask which is provided by the user. So also other than the face generation model, they try to also extend the work to the face editing. So in the face editing, we have two kinds of input. We have a target mask that we want to edit to, and we have also a target text. So we have an input image. For example, let's look the first image. An input image, and a target mask, and we try to edit this into different kinds of edited image. So by saying he's a teen, the face is covered with a short pointed beard. So we try to edit the female face into a male face. So which is very useful in editing the face very easily. Because in the past, people have been only using a unimodal editing system. It might be only mask or it might be only text. So this paper contains both the mask and the text-based face editing approach. So what is the motivation of this paper? So the motivation of this paper, I try to explain a bit. So basically, there's two motivation for this paper. So the first one is like most existing model do not support simultaneous conditioning on multiple modalities, such as text and mask at the same time. So this is the first motivation. The second one is supporting additional modality often requires time-consuming model, retraining, and extensive hyperparameter tuning, which is not preferable in general. So if you want to have a multimodality, we need to train into one collaborative model, and it requires a lot of hyperparameter tuning, which is not practical and in a very large scale. So what is the related work that I've been doing, that I've been done in the past? So one of the major work in the past is the diffusion models. So the diffusion model has recently become a mainstream approach for image synthesis, and they have a success in video generation, image restoration, and semantic segmentation. Also, they have a huge success in natural language processing. So, but this existing diffusion model only focuses on improving the performance and the efficiency of those diffusion model. For example, they try to enhance the architecture design and the sampling scheme. But in contrast, this paper focuses on using these diffusion models to collaborate or to provide a framework that we can use different unimodal frameworks into one framework. So this paper is doing something different in order to, rather than just generating novel models, try to use existing models just to include unimodal the diffusion models. So other related work we can mention face generation. So the following the GAN paradigm, the style GAN series boost the quality of the facial synthesis and provide an interpretable latent space for steerable style control and manipulation. So the style GANs has been successful in controlling and manipulation of different kinds of faces and generating their high quality correspondence. But like for this work, it falls into diffusion-based paradigm. So in particular, they try to leverage already pre-trained diffusion model for multimodal generation in editing. So they also mention some kind of conditional face generating and editing work. But this kind of style clips, diffusion clip, and there are also other many demonstrated remarkable performance in text-guided face generation and editing. But however, this kind of style or this kind of work, it only consists only a unimodal distribution or framework. So they don't provide a multiple modality. So that's why this paper is trying to solve that kind of problem. So let's look at what they try to contribute, which is a collaborative diffusion. So the authors proposed a collaborative diffusion to exploit the pre-trained unimodal diffusion model. For example, like in the past, people have been working on text-driven diffusion model, on the mask-driven diffusion model. So they try to use the already pre-trained existing unimodalities to achieve multiple modal conditioning without retraining them. So first, let's see the overall architecture. So given different kinds of modality, for example, for this paper, they only try to use two kinds of modality just to show it works. So for example, for this one, they try to use the mask and the text-based modality. And they also mention it can be X condition, which means it can be extended to multiple modality. But for the sake of this paper, they try to show only using two modality. So this collaborative diffusion at T, it uses XT, which is a denoised image, and they try to add the dynamic diffuser 1 in dynamic diffuser 2. So what dynamic diffuser 1 trying to capture is it trying to capture the influence function that is provided by the mask condition, and it try to use pixel-wise multiplication to produce some kind of intermediate image. And also for text branch, they try to use dynamic diffuser 2, which is responsible for capturing the influence of the text on the intermediate output. So they try to combine the dynamic diffuser 1 and dynamic diffuser 2 by using pixel-wise addition, and they try to get x sub t minus 1, and they try to use the denoising process to get the final sample x0, which is the synthesized image. So I will explain the architecture in a high resolution a bit later. So let's look at it. So first, let's just take a look at a unimodal conditional diffusion model. So because for their own paper, they try to use the already pre-existing pre-trained diffusion unimodal conditional diffusion model. So they don't really provide or retrain any kind of model. They just add their dynamic diffusion. So the diffusion process, which is also known as the forward process, it gradually add a Gaussian noise to the data and eventually corrupts the data XO, which is the pure given or sample data, into an approximately a pure Gaussian XT. At XT, which is the final step of the denoising process, the data is a pure Gaussian with variance schedule beta 1 to beta t. So Q is the normal distribution, which takes x0 as an input, which is the previous state, and it tries to produce a noised version as a current state. So it tries to sample a noise E to add into the sample data until it's turned into the pure Gaussian noise. So on this one, given xt, which is the noised version that we are trying to have or trying to output, we are trying to take the less noisy version and turn it into more noisy version until we have a pure Gaussian distribution. So this is also known as the forward process. We are just adding a little bit noise until we have a pure standard Gaussian distribution. So the reverse process is defined as a Markov chain where each step is learned on Gaussian transition. So Markov chain is based on the previous state, so that the reverse process is defined as p theta, which is the parametric denoising distribution. So for this one, it takes an x sub t minus 1, which is the noised version of that image, and it tries to clear the noise as much as possible using in each iterative step. So it takes the noisy version, x minus t1, as we can see here. Then it tries to predict the mean value of the less noisy version. So this is how they try to sample or frame the parametric diffusion distribution. So at the last equation, it tried to train the noise which we get from the forward process and the predicted noise that was used to generate the diffuse sample. So this is the training strategy. So for multimodal collaborative synthesis, in collaborative diffusion, multiple unimodal diffusion model collaborate at each step of the denoising process for multimodal guided synthesis. So the core of the framework is the dynamic diffuser, which is responsible for determining the extent of contribution from each collaborator by predicting the spatial and temporal influence function. So when they try to formulate the process, given the AIM pre-trained unimolar conditional diffusion model, they try to predict what kind of influence does each unimodal conditional diffusion model has on the final output. So they try to model some kind of dynamic diffuser to capture that kind of influence function. So this is their influence function D. So the D influence function, it accepts as an input xt, which is the noised version, and a time step t and a conditional modality. So once they have this one, they try to normalize it regularize using the softmax at each pixel p, and they try to use it for final prediction model. So for multi-model collaboration, they try to use M learned influence on the function IM, which is the regularized version of the dynamic diffuser, to control the contribution from each pre-trained diffusion model at each denoising step. So once they have the influence function, and once they have the predicted noise that was used to generate the diffusion sample. They use matrix multiplication to get the final predicted noise that was contributed to the final sample. So let's look at their algorithm for building their dynamic diffuser training. So this is the forward process I was mentioning before. So given x0, which is the sample data we have, and given the C1 to Cm, which is conditional unimodalities, it can be 1 to m, and given Q is the normal distribution. So this Q takes an input image x0 and different kinds of condition. It tried to sample noise from the normal distribution, and it tried to slowly add noise to the data until it changed into standard normal distribution. So here, line number 6, it tried to build a noise prediction model, which is EPRID-MT, which is the noise prediction model. This is trying to accept x0 as an input, which is the sample data, and it tried to predict the noise that was used to generate the diffusion sample. This is the reverse process of the diffusion process I was mentioning before. Then they tried to use a dynamic diffuser, which was responsible for taking an x0, which is the sample data, and it tried to predict the amount of influence does each modality have to the final output. So on number line number 9, they try to regularize this dynamic diffuser by using softmax at each pixel p, and they try to multiply to control using the matrix multiplication. Then they try to train using the L2 norm by comparing the loss between the actual noise that we add during the forward process and the predicted or the learned noise that we are trying to get from the neural networks that we are training. So this is the dynamic diffusion training process. So when they are trying to sample, they use the algorithm to start from the noise, the end noised part. So xt is the end of the first forward diffusion process, which is a pure Gaussian distribution. So it says from t equals to t, which is the end of the diffusion, the forward process, which we have a complete pure noise, and we try to sample some z, which is the noise from normal distribution, and we try to iteratively denoise the process at time step t. And it's the same thing until the line 10. So to the line 10, they try to denoise using xt. xt is the denoise version of time t, and using xt, they try to remove the noise which is predicted by the noise prediction model, and they try to subtract it, and they try to remove the noise, and like they try to add some kind of constant, which is z noise, and which is determined using before training the model. So during the sampling process, they just try to subtract the noise from the data to get the less noisy version. So that's they're trying to do. So like let's look a figure to make the concept a little bit easier. So this is their dynamic diffuser. Given xt, which is a noised version of their sample, they try to add a conditional modality in each step so that they would determine the influence function. So this influence function is responsible for capturing what kind of information does this mask have on the final output. So this mask is responsible for capturing the structure of the face, like the shape of the hair, the shape of the nose, or the shape of the mouth. So it is responsible for capturing what kind of influence does the mask have in the final output. So that's why they have the dynamic diffusion in the first place. So other than the face generation part, they try to extend their work in the collaborative editing process. So in addition to the additional framework, this framework is also capable of combining multiple facial manipulation, each of which is guided by different modality into collaborative diffusion editing. So in this work, they try to demonstrate such possibility by extending iMagick to the multimodal paradigm. So rather than just only generating face, they try to ask themselves, we can also include editing strategies on the dynamic diffuser to edit a face as the user wants. So this is their algorithm for implementing the collaborative editing. It's similar with the previous version, but they have some kind of input requirement. So in the first place, we have to have input image, which is X input, and we also have a target condition, which means like, first of all, we need to have some kind of expectation of the face it will look like, which is the target condition. A target condition can be a text-based or a mask-based condition. So we also have a diffusion model, like a diffusion model, which predict the noise. And we also have a dynamic diffuser, which capture the influence function in each step. So for number, if we can see number one, the line number one, it says from M1 to M, which is from different kind of modality, do the following process. So we have a target image and we have XT, which is we're trying to add a little bit noise to the input image until we have a normal distribution. And we also calculate the L2 norm, the distance between the actual noise that we added and the expected or the predicted noise that was used to generate the sample diffusion. And at the end of the line, at the end of 8, the line 8, it's just try to set up the sampling process. So for each T1, which is the end of the first forward diffusion process, which is the pure Gaussian distribution, and we try to sample some noise, and we try to denoise each process by giving some kind of little noise and subtracting from the xt, which is the current state that we have. So on number 17, they try to denoise x minus t, given xt, which is the more noisy version, and they try to subtract the noise from xt to get x minus t, which is, for example, if we have xt is number 4, and they try to remove the noise and try to change it to x3, which is a less noisy version of the input. And finally, they have x0, which is the synthesized image they want to sample. So let's look now the experimental setup they use. For the dataset, they try to use like 330,000 image in the Caleb HQ dataset in their corresponding annotated segmentation mask. So each mask has like different classes for different components. It can be hair, skin, eyes, and nose, and other accessories such as eyeglass and clothes. And this dataset also provide a rich and fine-grained natural language description for the image. So for the dynamic diffuser, they simply combine the mask and the text for each image without any kind of further processing. So the implementation detail, they adopt the LDM, which is the optimization objective for the unimodal diffusion model, because it have a good balance between the quality and speed. So their dynamic diffuser is a time conditional unit. For implementing dynamic diffuser, they use the unit because it's one of the easiest way to train the diffusion process. In fact, they argue that their dynamic diffusion is like 30 times smaller than the pre-trained diffusion model they have. So for evaluation metrics, they use the FID, clip score, and mask accuracy, and they also use like user study to actually measure the effectiveness of the quality using naked eye. So this is their quantitative result they have for the face generation part. So for the face generation, they try to compare their own work with Teddy Gunn in Composable. So in all metrics they provided, which is FID, text, and mask, as we can see here, their model was doing better than the previous state-of-art work they provided. And finally, they also used the user study for the face generation and face editing. So users says like more than like 70% of the users says their model is better in having image quality and conditional consistency, and also identity preservations. And about like 84% of them says like on the face editing part, which is have high image quality, and it is consistent with the provided conditional modalities they provide. So this is some qualitative comparison. So what they're trying to do is, given some kind of condition and given some kind of text condition, mask and text condition, they try to synthesize a very high quality image that is consistent with the provided mask condition. Yeah, for example, if we can see here, like she's a teenager, then for each different mask, they try to synthesize a very high quality image, as we can see here. So for the face editing result, so the input image, we have like input image, and we have like a target mask, and we also have some kind of target text, and we have to change, or we have to map between the input image to the edited image. As you can see here, between the target mask and between edited image, we see some kind of consistency, or we see some kind of alignment, which is what they are trying to do in this paper. So they try to also use like ablation study to measure their dynamic diffuser framework. So in dynamic diffuser, they try to add some kind of spatial variation influence function and temporal variation influence function. So the spatial variation, it only capture the mask-driven model, because on the mask-driven model, the mask is mainly responsible for laying out the shape of the face, the shape of the hair, and the shape of the eye. So which is very crucial for defining the structure of the face. So that's why they say this spatial variation is very important in designing their dynamic diffuser. So lastly, they try to also argue that their temporal variation is very important, because this is mainly responsible for providing additional text, skin text, like texture related expression. For example, especially when we are trying to have some kind of skin texture around the skin and the chin, the text-based modality is very influential in this kind of age. For example, if we say some picture has some kind of age and beard length, it's better described by the text rather than by segmentation. Segmentation cannot really capture expression-related feature of the face, because text-based are very powerful in expressing like wrinkles, scars, and moles. That kind of expression is properly captured using temporal variation of the influence function. So in conclusion, they propose collaborative diffusion, where pre-trained unimodal diffusion models collaboratively achieve multimodal face generation and editing without being retrained. They don't retrain the existing model. They just use dynamic diffuser to sample how much was influenced from each modality, and they try to use pixel-wise multiplication and addition to get the final output. So with dynamic diffuser, this framework could be used to extend arbitrary unimodal approach to the multimodal paradigm through predicting the relative influence of different modality. As I said, just by estimating the temporal and the spatial modality, they try to output the influence function that could be useful for the final output. So the limitation in the future work, since the framework focuses on exploiting pre-trained diffusion model, their performance is dependent on the capability of each model. So they cannot do anything more, because their model is trying to use the already pre-trained model. So the performance and the accuracy is relied on the existing pre-trained model. So the next future work can be is to train each collaborator on the large scale data set to perform a better accuracy or a better speed. So this is their future plan as of this paper. So thank you so much for your time. This is all about my presentation. If you have any question, now is the time.